Alright guys, can you start working on question 1, guys? Alright guys, question 1 is not really difficult at all. So if you haven't done it, just listen to me. It's not a difficult question, guys. Now you haven't guys listen, you have an observation from a binomial, and p hat is the estimate for p is defined by x by n, and we want to find the bias and the MSC. Right, the first, to find the bias, to find the bias, we use the definition, which is, this is the definition of bias, yeah? And yeah, you see that the expectation of a binomial variable is n times p. So you see you have p minus p, which is 0. So the bias is equal to 0. Yeah? Yeah? Easy, right? Now to find the MSC, because the bias is 0, the MSC is the same as the variance of this, which is the variance of x by n, which is, if you take the n outside, it becomes this. Now I'm sure all of you remember the variance of a binomial variable is np times 1 minus p. You guys remember this formula, right? So this becomes p times 1 minus p divided by n. And this clearly approaches 0 as n approaches infinity. All right. So hence, in conclusion, what you can say is that p hat is unbiased and consistent. Remember, consistency means that the MSE approaches 0 as n approaches infinity. Unbiased means that the bias is 0. So both properties are satisfied here. So guys, it's really easy question, right? And you do now question 2, please. Let's do 2, please. Anybody who hasn't signed the attendance sheet, guys. Okay, guys. Not really, because the expectation of xi is 0, but what we have is the expectation of xi squared. Right? No, everything can be 0. Because we have shown that each xi has its distribution. So here. So that means the expectation of xi is 0, and the variance of xi is sigma squared. Yeah. Yeah, exactly. This will be equal to 0. All right. So can we look at question 2, guys? So you have xi iid from this distribution, and you have an estimator which I call t. It's an estimator for sigma squared. So this is an estimator for sigma squared. Now we want to find, as usual, we want to find the bias and the MSC. Right. So first the bias. So this is expectation of t minus sigma squared. Now you can do any I mean, I'm sure you guys know that you can do any question in different ways. So I'm gonna show you. I'm gonna show you a different way of doing this than in the solutions. In the solutions, I have used a different way to do it, but now I want to show you how to do this differently. Okay. Now I'm gonna write you see what I've done here, guys. I have divided by sigma squared and multiplied by sigma squared, and you see why I'm doing this in a minute. Now let me pull out this outside so it becomes so this is different from how I did it in the solutions, guys. All right. Right. Now this guy here, if you look at this term here, you will see it. What you have here is it's a chi-squared variable. That's because if you look at, I know we haven't come to this stage yet, but if you look at equation 75, sorry, if you look at equation 75 on page 17 of the notes, of the lecture notes, you will see that this has the chi-square distribution with n degree of freedom. That's one of the formulas. If you look at page, if you have the notes with you, the printed notes I gave you, you will see that this is exactly a chi-squared variable with n degree of freedom. Now, one of the properties of a chi-squared variable is that its expected value is equal to the degree of freedom. So in this case, the expectation of this is simply n. That's yet another property is given on page 16 of the notes, where it says that the expected value of a chi-squared variable is equal to the degree of freedom. You should look at page 16 of the notes, guys. So I used that to get from this line to this line. So the n and the n cancel out, so this is 0. All right, guys. So you can see that the bias of the estimator is 0. All right. In other words, the estimator is unbiased. And this is once again, this is different from how I did it in the solutions. Now, to find the MSC, because the bias is 0, you can say that this is the same as the variance of t. Yeah, and this is the same as the variance of and this you can write. I'm going to apply the same trick as I did in the first part, right? So I'm going to write this guy here as like this. All right, so you see I have multiplied by sigma squared and divided by sigma squared. The same approach, the same trick. Now you can pull out this constant outside, so it becomes this times the variance of this guy, which is once again by equation 75 on page 17. This guy here is a chi-squared variable with n degree of freedom. Right? This is now another property I'm going to use here is that I think I mentioned this to you guys before, that the variance of a chi-squared variable is 2 times the degree of freedom. So in this case, the variance of this is 2 times n. That's a property, once again, it's on page 17. It's on page 17 of the notes, right? So this simplifies to 2 sigma 4 divided by n, which as n approaches infinity approaches 0, right? Hence t is okay, guys. This is, I know this is not the way I did in the notes, sorry, in the solutions, but I just wanted to show you a different way of doing things. I hope it is clear. Are you okay, guys? Yeah. Can you do question 3, guys, now?
say x times this function from delta to infinity. No, you don't need to. You only do this. Just ignore this part. It shouldn't be there. So just cross this part. It's only the M and N. Just find the M and N. Yeah, you need to do that. Yeah. This is the restricted domain question. You know the one we talked about yesterday. Yeah, restricted. Yeah.
All right, guys. So you have the first part is you have an estimator which is x bar, and x bar is an estimator for delta. We want to show that the bias of this estimator is different from 0, right? Okay, this is the definition of bias. This is equal to this, right? And equal to this. Okay, I guess listen to me. This is question 3 I'm doing, guys. Now, how do we find the expectation of xi, guys? You are given the density function, so you need to simply integrate the density function to find the expectation, right? So this is 1 over n times the sum of the integral from delta to infinity of x e delta minus x dx minus delta. Now, I guess by now all of you are experts in integration. So how would you do this integration, guys? I know there are a number. Well, you could use parts. I think, but I would prefer using a substitution. I'm not a big fan of using parts. So if you do the substitution, then y equal to x minus delta, then x equal to y plus delta. Okay. All right. Put this sub into this. You get 1 over n times the sum. The limits of integration go from 0 to infinity. X will become y plus delta, e of minus y, dy minus delta. All right. So now what you have here should be a familiar integral for you guys. Now, let me ask you, these two integrals should be familiar to you guys. This integral is what? Is equal to You guys see that? Yeah. You remember I talked about the gamma function couple 2 or 3 weeks ago in the class. So this is gamma at 2, and this is gamma at 1. And gamma of 2 is 1 factorial, which is 1. Gamma of 1 is 0 factorial, which is 1. Alright? Alright, so what you have is 1 over n what you have is 1 plus delta minus delta, alright, which is 1 plus delta minus delta, which is equal to 1, which is not equal to 0. Alright, so the estimator is indeed a biased estimator for delta. Now to make it an unbiased estimator, I think I did questions like this before, guys. We need to define a new estimator so let me call it y. I mean, you don't need, you can call it whatever name you like. So I'm going to define a new estimator y called x bar minus 1, and this new estimator y will be unbiased because the bias of y is the expectation of y minus delta is the expectation of x bar minus 1 minus delta, which is the expectation of x bar minus 1 minus delta. This is 1 plus delta minus 1 minus delta equal to 0. Alright, so this implies that y is an unbiased estimator. Right. Now, finally, we need to find the variance or the MSC of the new estimator y. All right. Okay, that's what I'm going to do now, guys. So, so I want to find the MSC of the estimator y. The MSC of which is, because y is unbiased, it's the same as the variance of y, and this is the same as the variance of x bar minus 1. Remember, the variance of x bar minus 1 is the same as the variance of x bar. I'm sure you remember this, guys, right? That adding a constant or subtracting a constant does not make a difference to the variance. So the variance of this is the same as the variance of this. Yeah? Okay, so okay. Okay, guys, now to find the variance of xi, I'm going to use the traditional formula. I'm sure you know. It's the expectation of xi squared yeah. Now we already found out, we already know what the expectation of x sub I is, right, from the previous part. So so what remains to be this guy is, we already know, is 1 plus delta squared. Yeah. So what we need to find is the expectation of the square of xi, right? So we can find that in the same fashion as I did before. Okay, so this will be integral from delta to infinity of x squared e delta minus x dx. Yeah. Now to do this integration, once again we make the same substitution, that y equal to x minus delta. So if you make this substitution, you get this is what you get. Now if you open the brackets here, you get three terms, right? Y squared. So you get three integrals basically. You get three different integrals. The first integral will be 0 to infinity of y squared e minus y dy. The second integral will be 2 delta and the third integral will be are you guys with me? Right, you get, because when you expand the brackets, you get three different terms, so three different integrals, guys. Each of these integrals is a gamma function. This integral here is the gamma function at 3, and this integral here is the gamma function at 2, and this is the gamma function at 1. And we know the gamma function at 3 is 2 factorial is 2, gamma function at 2 is 1, and gamma at 1 is also 1. So it becomes 2 plus 2 delta plus delta squared minus 1 plus delta squared. Yeah? Now if you a lot of the terms will here cancel, so you get the answer you will get is this. And this approaches 0 as n approaches infinity. Alright, so hence x bar minus 1 is unbiased and consistent. Is this clear, guys, or not? Yeah. Sorry. Is anything not clear, guys, here? Yeah. Can you do question 4, guys, now?
Yes. Next week, what about you? You're here.
question 5, 6, and 7 are for next week example class, okay? So it's only question 1 to 4 are for this week. I know I didn't say that, but in the email. But question 5, 6, 7, we will do that next week. So don't worry if you haven't done them. I know some of you have already done 5, 6, and 7, so that's good. But if you haven't done those, don't worry. Okay, we will do those next week. Okay. No, there's some more from the next, for the next problem sheet. Yeah, I know you guys have already done it. That's very good. Yeah, that's very good. Yes. All right, question 4 is not really difficult. It's not. So you have guys, could you listen please if you haven't done it? Question 4. So you have the lambda is the parameter of the Poisson distribution, and we are estimating it by the sample mean x bar. The first one, we want to find the bias. We want to find the bias of the estimator, which is this. Yeah, and the expectation of xi, you guys remember well that the expectation of a Poisson variable is equal to the parameter lambda, right? So this is 1 over n which is so the estimator is unbiased, right? Now to find the MSE, of the parameter sorry, it's the same as the variance because the bias is 0, and this is Okay. Now taking the variance inside, guys, you get this is 1 over n squared, right, times the sum of the variance of xi. I'm sure you guys remember that the variance of a Poisson variable is also equal to lambda. So what you have is 1 over n squared so this is equal to this, right? Okay, guys, and this is lambda by n, and this approaches 0 as n approaches infinity. Hence, x bar is all right. If you haven't done 5, 6, or 7, don't worry. We will do questions 5, 6, and 7 next week example classes, and I'll plus some more questions, right? So if you haven't done those, don't worry. Okay.
Little value on the variance. He intention that we will find the bias. He zero the value equal to lambda, right? Yeah. And here we'll find the variance of x bar here. And could we just say that because of the variance of body distribution lambda, so equal to lambda, no?
This is x bar. X bar is not the same as x. X bar is not the same as x bar. It's a sample mean. It's different from x. So you cannot say that this is equal to lambda. Yeah. You didn't catch it? Okay. I'll put it online later on so you can see, but this one, yeah.
Αλλά κάνει ξανά νιώσα τις εικόνες του μάλλον. Επειδή
They're the same. I think both of them are the same. So we're finding one for